Tian Yanchang is a third-year PhD student in computer science at MIT, advised by Professor Bill Freeman. He had research experience in machine learning, physics-based vision, computational imaging, and computer graphics. His current focus is on video generation and infinite context learning. Yeah, it's your time, Tian.
Thanks for introduction and hosting. Today I want to talk about long context modeling through test time training. Nowadays, all the foundation model around us are sequence to sequence models. It takes a sequence of input, sequence of tokens input, and output another sequence of tokens as output. And here, the sequence of tokens can be data from any modalities, can be text, image, audio, videos, etc. One important dimension for such model is the sequence length dimension. It means how many tokens the model is processing all at once. And the foundation model's sequence length is increasing very rapidly. The newest version of Gemini this year supports 1 million tokens as input. And such long context model already have a lot of applications like long document understanding, long reasoning chains, and also long interactive video generations shown by Jenny 3 last month. However, current sequence-to-sequence model have several limitations. It has no memory of previous experience. We are using them in a per episode based usages. Second, it can only generate outputs after receiving some input. And third, if you think about these models as living beings, as having real life, their lifespan is basically how many tokens they are processing. And for models with short sequence lengths, it basically means it's living beings with a short lifespan. And for living being with short lifespan, it's hard to evolve into different type of interesting behaviors. So I think in the future we will need something I call it as lifelong machines. It would have a much longer memories, and we have probably memories of all the episodes we have in with them. And it will be always online with probably near infinite sequence length. And such living beings will definitely have a significantly longer lifespan. And this longer lifespan provides a basis for it to emerge uh, out of a lot of interesting behaviors. So to build such lifelong machines or machine with long-term memories, there will be a lot of challenges. There will be challenges through the model architectures on training data and also on training strategies. Today, what I want to mostly talk about the model architecture level and through the through the prospective test time training. So to talk about architecture, let's start from transformers, the most popular sequence-to-sequence models. Its core operation is basically attention. And the attention has a property that it does not compress any in-context tokens. It keeps a key value cache of all previous tokens it has seen. And when a new token came in, it will globally random access all previous token. It basically look up every token and compute a weighted sum as output. And such operation has increasingly, linearly increasingly memory and compute footprint for every new tokens. And so we can see that such operation is expensive at a long context. And second, it's impossible to serve infinite sequence lengths. And this motivates people to find a lot of new sequence models. And RNNs in recent years became popular again because they have linear cost. So RN basically have two operations. At every time step, there's new token came in. It first updates the states using the current token. Right? The second operation it has is basically with the current states, with current input, how to compute current outputs. And then you can do this at every time step. So there are just two operations, state update and memory readout. Let's closely look at the most simplest form of RNN, linear attentions. And here I will show some connections between RNN and the test time training in the later few slides. So linear attention basically removes the softmax in standard attentions. And when you're doing linear attention causally on input sequence, it can be written in this recurrent form, basically in the RNN form. And it has a state of shape d by d. It's a matrix state. And the state update equation at each time step will be a rank 1 matrix updates. And its memory readout operation is a matrix vector multiplication using the state to multiply current input tokens. Okay. So uh, one interesting perspective came. Let's think about this state not only as a state of Rn. Let's think about that as the weights of a linear neural network layer. F is a linear layer. S is the weights. Then we can see that the memory readout operation is basically the forward pass of this neural network, this small, tiny linear neural network. A more interesting perspective came. If you think about this as not only as a weight, it's a trainable weights of this linear neural network layer. You will see that the state updated equation is actually one step of a gradient descent. I will show the loss. I will show the loss function. It does a gradient descent. So the loss function will look like this. It basically says if you forward pass through this and compute negative dot product between this, if you use this as loss function and you do one step of gradient descent on this state S or on the trainable weight of this linear layer, it gives you the state update equation. Okay. So I will show this in next slides more closely. And some people may be wondering, okay, is this some tricks, some algebra tricks that you just make a superficial loss function and through some derivation it looks like that. Does this loss function make sense? And I will explain this in next slides. So if we look at the equation we see before through some diagram, suppose we have k tokens here and the value token is a kv pair here. And this is a linear layer. Its weight, its trainable weight is S. And suppose we first do a forward pass by feeding the keys to this layer, and we predict something out. Let's call the output as retrieved values. It's just a forward pass of this linear layer. Okay. And now, if you compute pairwise loss between retrieved values and the values, the pairwise loss like this, the negative dot product loss, and then you compute gradient descent to update the weights, it gives you the state update equation showing last slides. Okay. And if you look closely what this loss function is doing, it basically says the retrieved values should align with the values. Right? It is encouraging the predictive values to align with the values. And in other words, this whole gradient descent basically try to train this linear layer to memorize the mapping from key to values. You give me the key as input, I will give you something very similar to the values. Right? Try to memorize the mapping from key to values. And this weights, we typically call it fast weight because it adapted the test time to store temporary memories. So this is a close lookup at linear attention. And this is actually, we already say something like test training, and which I will explain later more closely. Another thing in that we just talked about linear attention, the vanilla linear attention. Recently, there are a lot of variants of linear attention that are popular. For example, Mamba and DeltaNet. And I will show that it can be understood through the same framework by just changing the loss function. It's still a linear fastway function, and it's just doing gradient descent under different online loss functions. And for Mamba 2, it introduced a scalar decay at each time step. And you can think about this scalar decay as adding a weight decay term on these online objectives. And for DeltaNet, its state update equation looks a little bit more complicated, but actually through the fastway perspective, it's only changing the online objective through dot product loss to L2 loss. Okay, so we talk about some examples linear attention and how it can be understood through doing online gradient descent. And here I give you a more detailed formulation of the testing training for RNNs. Suppose we are processing an input sequence that has n tokens, x1, x2, xt, each token a d-dimensional vector. And we follow the notation of a transformer. We split each token into query key value. And suppose we have a fast wave function. It's a parametric function. This function can be anything. It can be a small linear layer, it can be an MLP, or it can be a very big transformer, it can be anything. It has a trainable weight of W. We call it the fast weight. It's adapted online to store memories. And to design RNN, we use gradient descent as the update equation. Okay, we use gradient descent to update the fast weight, and we call the state update. This fast weight is state, this fast weight is trainable weight. It's basically the same thing. And if commonly, people have been using loss functions or like L2 loss, dot product loss. It's all about key-value associations. It's all about implementing associated memories. And to show a diagram of this is suppose we have the KV cache of previous tokens. We compress them into the memory module. It basically compress them into the fastway function through gradient descent. Then when a new query token came in, we don't interact with KV cache directly. We just do a forward pass through the memory module to compute the output. So that's about understanding RNNs through the prospective testament training. I can stop here a little bit if you guys have questions.
So how many gradients descent steps do you need per forward pass?
Yeah. So the question is, we are saying that we want to use gradient descent to compress the KV cache into the fastway functions. How many gradient descent steps do we need? Typically, throughout this paper is one. Majority of the fields is using one step gradient descent. I've been trying using multiple gradient descent. It's a little bit unstable.
But if you just use one step,
That's the one.
loss is not zero, then you are not actually doing the accurate attention, right? So you assume loss is zero, then KV is equivalent to the original transformer attention. But if you are just doing one step gradient descent, the S is not the same as KV.
It's not the same. If you do this updated equation multiple steps, and suppose the loss is zero, what it will do is it will be much similar to softmax attention, or even much
Yeah.
similar to the hardmax attention. But now it's not. It's a
So it's a approximation.
you can think of a approximation. I think it's just a different inductive bias. It's always about associating k with values, but you want to approximate that with softmax kernels or with some other ways.
Okay. Yeah, thank you.
Mhm. Okay. Uh, my understanding of testament training now, it's interesting because it actually opens a very big design space. You can change the fastway function from linear to MLP to anything you want. And you can change the testament training objectives. You can change that from the key value association loss we see to maybe next one prediction loss, or maybe to denoising loss. You can just do whatever you want. And you can also change the testament training optimizers from the vanilla gradient descent to something more advanced. Right? Nobody uses vanilla gradient descent nowadays in pre-training. So it basically opens a very big design space, and we have shown in previous slides, linear attention, Mamba, delta net is just one point in this large design space. And then Dolly, we can definitely find something more interesting and more powerful. Uh, so let's move into the to this specific work we have done and test some training done right. It's a joint collaboration between MIT and Adobe Research, and done during my part-time internship at Adobe this spring. So this work, to start introducing this work, I want to talk about the concepts of hardware efficiency. Transformer is very successful. One reason that attention can be implemented very efficiently with high parallelism and very efficiently. And the flash attention 3 can achieve hardware utilization about 50% to 70% on H100s. But when designing new architectures, it's actually very non-trivial to achieve such high efficiencies. And a lot of RNNs cannot be trained efficiently, especially the older generation of RNNs like LSTM. And recent years, people realized that linear arrays, basically linear attention, Mamba, all these variants, can be efficiently implemented, can be trained parallelously. And the reason for that is linear RNN has associative properties. I will explain this a little bit. It's just one piece of the reasons why linear RNN can be implemented efficiently. I think it's a major piece. And if you don't fully understand, I think that's fine. It's not a concept that normal people without background can understand in 10 seconds. So linear RNN's state update equation is associative. Suppose you have 4 tokens and you want to update its state iteratively through 4 steps. You actually don't need to compute them sequentially. You can compute in any order. You can compute parallelly. For example, if you have 4 items and want to do some associative operation, you can just combine with any, you can segment in any segments and combine each segment, compute each segment parallelly. And that's basically associative property. However, nonlinear RNN is not associative, and such strategy of parallelizing linear RNN cannot be used for nonlinear RNNs. Okay. And more importantly, if you look at the design space of tensor training, it has some overlap with linear RNN, but a majority of the design space is nonlinear. And nonlinear cannot be efficiently implemented with that strategy. So to fully realize the potential of tensor training, the vast design space to fully explore the vast design space of tensor training, we need to find ways to scale up nonlinear RNN to make it more efficient. And this is what this work try to do. So how to do that? I will talk about through 3 perspectives, and actually all of them leads to one simple solution. So to design an algorithm that can run efficiently, we need to care about, on GPU, we need to care about tensor cores. If you look, this is the specs for H100s. If you look at that, it says it can do a lot of floating point operations. And actually, all of them is done through tensor cores. And the tensor core can only do dense matmos. What does that mean? It can only do 2D matmos, basically. And there are some restrictions on the minimal size of these matrices. And this also tells us that if we want to do matrix multiply with a single vector, it's actually leads to low utilizations. You either need to lot of paddings or you either don't use tensor core. And what does it mean for tensor training? For in tensor training, we are computing some gradients like this. The f is a fast wave function. We're computing gradients like this, and the key value are just the vectors. This w are matrices. And if we want to compute gradients for one single token, it's basically all about matrix vector multiplications. There's no matrix multiplication. There's no matmos, which means if we want to compute gradients for one single token at a time, it will lead to low hardware utilizations. And this has been realized by several previous work, which they say, okay, I'm going to use an online miniBus of 16 so it can exactly be the minimal requirements to use tensor core. Basically says, okay, I'm not going to compute the gradients at 1 token at a time. I'm going to compute the gradients for 16 tokens at a time, such that it's matrix multiplications here. And the minimal size of this matrix is going to be 16, basically the minibar size. So that's one aspect of tensor cores. You need to make mostly the operation as matmos rather than matrix vector multiplications. Another property is about arithmetic intensity. We not only need to look at how many floating point operation can be done, the compute speed, we also need to look at the memory speed. For H100, the big says it can load 3 trillion bytes from the HBM to its cache, which will be further used to computation. And it basically says, here I use half of the number because this is the floating point operation you can do per second for dense matrix multiplications. It basically says on H100, the time it takes to load 1 byte from HBM can be used to do 300 300 flops, 300 computations. And it basically says, suppose you are designing a new architecture. If your new architecture have way more compute than the memory load, it will be fine. But if your new architecture can only do maybe 100 computes per loading, it basically says the arithmetic intensity is lower than 100. It basically says it cannot be efficiently parallelized. And for test time training, the arithmetic intensity, basically the flops divided by the memory loads, is always smaller than the test time training bar size. It's always smaller than the number of tokens you are computing test time gradients all at once. Uh, Another perspective is about the number of parallelism, the degree of parallelism. If you look at the training of modern models, there are three dimensions that can be parallelized. One is batch dimension, one is feature dimension. Basically, you can see model channel dimension or the has dimension. It's the same dimension. Another is sequence length dimension. And then for majority of the architecture, the batch dimension and the feature dimension can be trivially parallelized. It's just not too much computations, too much communications. But for a lot of architecture, it's very hard to parallelize on sequence length dimension. And here, some people might be curious. You list the three dimension to do parallelization. Will that be enough if it can only be parallelized on batch and feature dimension, right? Will that be enough if we can parallelize on this two dimension and without parallelism on sequence length dimension? Your answer is no, because when we really are training long context models, the bar size is typically one per GPU or one per hardware, which means it can only parallel on this feature dimension, which is typically has dimension. And for modern models, it's like 12 heads, 24 heads to like 48 heads. And for one piece of A100, it has 100, 108, 108 independent compute units. Being able to only parallel on heads dimension will not be able to soak up all the parallel computing units. So you need some parallelism on sequence length dimension.
Can I ask one question?
Oh, what's your question?
Yeah, so do you find usually utilization to be lower while doing test time training with one batch size and longer sequence length?
Yeah, if you are doing if you're doing the original test time training, if you're doing original codes with threading kernel implementation, if you are doing bar size one, it's lower. So when I was testing the flops, basically I increased bar size from one to two. The flops utilization basically doubles.
Okay.
That basically means you are not using all the streaming multiprocessors on one single GPU. Half of them is basically empty. Okay. And if you're doing bar size one, you can only parallel on this feature dimension for the original testament training, for the has dimension, which is typically 12 or 24. And if you're doing parallelism on sequence length dimension for nonlinear testament training, it's basically you can only do parallelism within the batch, within the testament training batch size. Okay. And actually, our three previous discussions basically lead to a common solution. We want to use a large testament training bar size. And by large testament training bar size, it means that we want to compute this fast weight gradients for a lot of the in-context tokens all at once. And by doing this large chunk testament training, large bar size testament training, we can definitely use a lot of mathemals. And also, you will have a much higher compute intensity, right? And also, you have high degree parallelism because suppose you are using 1,000 tokens to compute the fast weight gradients. The computation uh, at this 1,000 tokens is parallelism. It can be parallel. And in most of our experiments, we use about 2,000 to 1,000,000 tokens to compute fast weight gradients. And I think a more interesting stuff in that, if you're doing this large chunk test time training design, you don't need to write kernel codes. You can only write PyTorch code with high enough GPU utilizations. And this actually makes your research iteration much faster. You don't need to write kernel code. If you can write kernel code, it's better. It will be more efficient, especially about memory efficient. But if you don't want to write, that's fine. Uh, So down with hardware efficiency. Another interesting perspective when you think about new architecture is about the data topologies. So if we look at this large chunk tensor train design on the right, it basically says we're gonna split the input tokens into a lot of chunks. Each chunk can be 1,000 token, 2,000 token, or 1 million tokens. And for every chunk of tokens, we're gonna update the fast weight once and do this memory readout once. Okay. And it basically says this architecture ignore the orders within the chunk, right? When you are doing batch gradient descent, the tokens within the batch are orderless. It's a set. There's no orders here. So it's orderless within chunk. And when you are doing gradient descent across multiple steps, it's naturally causal between chunks. So put it more plainly, this architecture is more suitable for data structure like a sequence of a set. You have a set of tokens, no order within set. You have another set, you have another set, you have another set. And within set is causal. Okay. But not too much data topology follow this. So how to deal with different data topologies? One thing is that you can add positional encodings within the chunk, right, to to help you to model token ordering or data topologies within the chunk. A second, you can use window attentions within chunk or cross local chunks to help you about data topologies within chunks. Another reason why we use window attentions through this project is that a lot of people realized all this linear attention, all this tensor training, all these compressive based RNNs is not efficient or it's not effective enough when handling localities in the data. Look, by locality, I mean within this small piece of receptive field, you probably want global random access. You probably want precisely looking at every token. And all of the linear attention RNNs is not actually very effective at this. And attention is much more effective at this. So we do want to use some local attention. Another thing is that if you don't use local attentions, a part of your state size will be reserved for local memories. And the local memory is about constantly swapping in new local memory and swap out old local memory. Right? And it's faster changing. And then people realize that for linear attentions, if you have some locality handled by window attention, your long-term memory will be much better. There's some work on this. And that's the second reason we use window attention parallelly with this large chunk tensor training, not only for the positional encoding within the chunk, but also for better long-term memories. And done with some of the high-level ideas and some details about this tensor training, we are using a three-glue MLP as a fastway function. It's a three linear matrices as basically as RN states. It has one nonlinear here. And we are using the online training objective as we showed before, the negative dot product loss. And we do one gradient descent followed by a L2 norm on these weights. Basically, you can think about adding some norm somewhere in your model will make the training more stable. And we show that this architecture can be used for three different data modalities. One is novel view synthesis, which is processing set of images. And one is language models, and one is autoregressive video generations. I will start from the experiments of novel view synthesis. So by novel view synthesis, this task means, suppose we have a lot of images here as inputs, showing on the bottom of this video. Or more vividly, suppose you take images of the room around you, take 100 images of the static room around you, and suppose you have a camera pose for each images. And you pass through the image and the camera pose through a neural network, and the model will be able to render any viewpoints in this room. This is about novel view synthesis. The input is multi-view pose images. Right? You have 100 images, give that as input. And you also put some query camera pose in the input. You ask the model, what's the novel view of this room here? You give it here as a query tokens. And the model should be able to output novel view RGB. It's like a machine translation. You give some piece of context and ask what is that in English or what does the room looks like in this viewpoint. The model gives you RGB as output. We done at two different data sets. One is object-centric and one is scene data set. You can imagine that the scene data set has more content, has a larger field of view, which is more challenging. So some people, actually a lot of testing training people are doing language models. And so when I explain what I'm doing to them, a lot of them will ask why you are using this novel view synthesis task. So this task is actually very interesting. I typically call it as smart retrieval task. So it has two problems. One is smart, one is retrieval. What does that mean? The retrieval means, what is a retrieval task basically means? All the information you need to answer the question is already given you. Right? All the information about the novel view is already given you. It's not a knowledge task. Knowledge task is like, what is the capital city of the United States? You either know it or you not. Retrieval task is all information is given at you. You just need to regroup the information and answer my question. Second, why I call it smart retrieval? Because to answer this question, you cannot do by simply copy paste. You need first to realize what's a 3D structure, then re-render it. So it's a smart retrieval task. And second, a major difference between normal retrieval tasks in language models. Normal retrieval task in language model is like in a very big paragraph of text, there is one sentence saying, please remember this number. I will ask you later. And in the end of the paragraph, after the model have read this paragraph, the user will ask model what's the number you memorize. The difference in that, this task has compressions. This task does not require global random access. Language model retrieval task can say, what is the first sentence in the second paragraph? Or ask, what is the sentence in the last paragraph? It requires global random access. And for novel view synthesis, it do have some global random access, but it's a lot of compressions. Because every patch you have seen probably exists about 10 times. You have a lot of compression you can do. And the third reason I'm using that is this task you can control the difficulty by using different resolution, different number inputs. Okay. There are some other reasons. I will jump on now. So to show how we use testament training to do this task, suppose we have input post images like this. Suppose we have 3 input post images. All of them have some per image local attentions. And after this kind of per image local attention, we concatenate all the tokens from every images. Right? Suppose you have a lot of 128 images, it has 1 million input tokens here. And with all of them token, I will use one gradient descent to update this fast-way sweep glue MLP, to update this memory module. And after that, when novel view query token came in, when novel view camera pose came in, this query token will enact. We also have a pre-image local attention. And then it will directly query this fast-way MLP to render the novel views. So this compute has 2 stages. One is prefill. You have a lot of input images. You use test training to materialize or to update the fast weights. That's prefill. And after prefill, all the input images can be removed. It's gone. You don't need to keep it cache here. And when you are rendering novel view, you just do forward pass with MLP. And actually, very interestingly, when you are rendering novel view, the model is just a standard VIT, very image transformer, with the MLP weights fixed because it's already done the updation. We call it the memory update as a prefill. It has linear complexity because it's a linear cost Rn, and it's processing all input images all at once. And the memory readout is decode, it's rendering. And the decoding is fixed cost, no matter how many input images you give to the model. And it's a standard same size VIT, and it can be run around 37 IPS on A100 by just using Petrol to test the speed. Adoli can do faster if you have some post-processing. And to compare with, we definitely need to compare with full attention baseline. The full attention will remove this testament training layer with 2 attentions, right? To resemble the prefill and decode process. The prefill process will be all the input images will look at each other. All the input images have a self-attention. And the decode stage will be the novel view tokens will crossly decode or crossly attend to input tokens. So that's a full attention baseline. I think it will have state size linearly growing within the number of images. And the prefill compute is quadratic because the self-attention within all input tokens. And the decoding compute is also growing linearly. A more important baseline is this, is register attention. It's about using softmax attention to do compression. So it has two attentions within each block. The first attention, we also call it prefill. It do joint bidirectional attention between input images and a set of register tokens. Okay, it's input register attention. It's basically try to compress the information in the input token to the register tokens. And in the decode stage, the novel view query tokens will not look at the input images. We will only look at the register tokens. It's basically using the register token as a bridge or as the information bottleneck. And this is a baseline for using attention as compression. And the result is actually very surprising. When we use attention as a compression baseline, it has linear compute cost in decoding, but the performance is much worse than the reliance using test time training as a compression. That's one point. The second point is using test time training as a compression is basically always behind full attention on this novel view synthesis task. And I think it makes sense because this novel view synthesis task is a smart retrieval task. And when you are doing some type of compression, you definitely lost something. And that's why it behinds. And this is done on the object data sets. And here, if you redraw this figure, where the axis is prefill time, you will see linear method definitely much faster. Another interesting results we realize is when we are doing on these thin data sets, we try to compare this data-driven novel view synthesis methods with 3D Gaussian splatting, with a heuristic-based, optimization-based graphics methods, 3D Gaussian splatting. And actually, when up until 128 images on the thin data sets, our performance is higher than the 3D Gaussian splatting. And I believe if we get better data sets and better training strategies, this data-driven novel view synthesis methods will constantly be better than this 3D Gaussian splatting-based methods. Okay, so let's jump to the language model experiment. And here, one big difference is the language data is causal. It's per token causal. It has strict causal structures. And the novel view synthesis data does not have causal structures. Another problem about language models, what is a trunk structure? There seems no trunk structure in languages. Then how are you going to do large chunk test time training? So we do it very simply. We just use a hyperparameter defined chunk. Every 2,000 tokens, we will update the test time training weights, or every 4,000 tokens, I will update the test time training weights. The second problem when using large chunk test time training to language model now, the test time training layer cannot implement per token causality. The states is updated every 2,000 tokens, every 2,000 tokens. There is no per token causality. So to do that, we use a sliding window attention to handle the causality, per token causality. Specifically, suppose here is your input tokens. We split into two chunks. Each chunk have 4 tokens. And whenever a new chunk of token came, it will first be used to if you use this chunk of token to update the state first, then do the memory readout, you are doing this blockwise causal mask, equivalent to the attention mask. But if you change the order between the state update and the state apply or the memory readout, you're shifting the blockwise causal mask. And this shifted blockwise causal mask is used in the language models, such that It maintains causality. Right. So in the experiments, I compare with several baselines, several linear attention baselines. I think the results we can jump now. The interesting thing came when this metric came. So I want to take a few minutes to explain this figure. When you do a long context modeling, one metric people want to use is such figure. It's called proposition next token prediction loss. It's a validation loss plotted at different token positions. It basically says if I give you a piece of a sentence and it has 32,000 tokens, and can you show the next token prediction loss on every position? And if you look at this blue line, that's the performance of a full attention. The next token prediction loss is always decreasing as you have more and more tokens, which means the transformer is using the context effectively. Because given more in-context tokens, the next token prediction loss should drop if your model can memorize previous tokens. And if you look at this curve for sliding window attention, which is a gray line, the sliding window size about 2000. Its loss will flat after about 4000 tokens, which means sliding window attention has no memories of a previous token. It cannot effectively use all the in-context tokens to aggregate information to help you on next token predictions. And if you draw that for different linear attention, they have different slopes. And it's very informative to show such figures when you are comparing with different RN or attention methods. So I think that's the key figure to understand. Another very interesting figure is about state size scaling. Suppose we increase the size of the fastway, will the performance go better and better? And this is actually true for language models. Here is the validation loss, and the x-axis is basically state size in log scale. Okay, I will jump over several experiments and show some interesting stuff.
Can I ask something?
Yeah.
You showed the loss curve. Does it also improve the performance in like long-term recall sort of tasks?
I didn't show that. So I show the loss here. I didn't have data for that experiment use. We do have some evaluation on the ruler benchmark on retrievals, and we show difference that more advanced optimizers have better performance on this long context recall. But I believe this is also true for larger state size, but I didn't do any experiments on that.
Yeah.
There are some other interesting ablation I want to show here. So again, with state size scaling, I just showed one plot on language model. Here is another plot on novel view synthesize, where the x-axis basically means how many input views you are using, and the y-axis means novel view PSNR, novel view rendering PSNR, and different curves mean state size, different state size. And here is the smallest state size, here is the largest state size. Basically, the higher the state size, the higher the PSNR. This is a little bit trivial because higher state size give you much more flops. Your total flops also increase a lot. And here's experiments for language models. It's similar phenomenon you have seen. And here is another interesting ablations. So we mentioned that tensor training has a very large design space. You can play with different design choice. You can change your tensor training optimizers. In the beginning of this project, I don't believe that. I saw tensor training optimization may not matter. Maybe gradient descent is enough. But later, when I try to switch from this vanilla gradient descent, this yellow curve, to some different optimizers such as momentum or more, the performance is basically always better. When you use more complicated optimizers, it seems that the performance is consistently better, especially more has a much better performance, not only on loss curve, but also on retrieval task. So that's some interesting ablations. And here, I want to mention one major limitation of this large chunk tensor training. If you think of through another perspective, what we are doing here is we are doing some trade-off. We are trading the number of recursive steps for parallelism. Right? For example, we are saying, hey, You don't need to update states so many times. You just update a much fewer number of times. So we will have higher parallelism. So we are treating depth of recursive for parallelism. And ideally, such trade-off is not free. Such trade-off should give you lower performance on tasks which needs a lot of recursive steps. And such trade-off is very favorably if you are doing tasks which does not have then recursive steps. I think which is for a lot of computer tasks. So here I show it. Uh, Here is about test time training or linear attention. This light blue line is member. Is bidirectional member. By bidirectional, I mean stacking two blocks of a member, one at this direction, one at that direction. It's basically is a linear test time training with per token recursive steps. And this another blue line is a linear large chunk test time training with the same state size, or slightly fewer flops. And you can see on variant task, this large chunk design is basically free. It gives you better performance and better efficiency. But for language, this is not the case. When we use a linear large chunk test time training, and when compare with this yellow line, when you compare the blue line with this yellow line, the yellow line is basically getting linear attention with the same state size. It's a per token causality linear memory. The performance of linear chunk is basically much worse because the language have a lot of recursive steps. But the story will change a little bit if you use nonlinear large chunk and a more advanced optimizer. You can catch up. You have high efficiency and you have higher design space, so you can catch up by doing some other stuff. That was the story for the limitation. Another interesting relation, actually, I forgot to show, is about when using linear fast weight and when using nonlinear fast weight. And here's the comparison. And in these two experiments, the red line is the nonlinear fast weight memory, and the blue line is linear fast weight memory. We make the linear fast memory to have much higher state size. So the flops linear fast weight memory and the state size, the linear fast weight memory, is always larger than the nonlinear ones. But the performance in experiment we show that nonlinear is consistently better. So I think I'm mostly done with the material. And if you guys have questions, we can discuss. And if you don't, I can share some other comments and other personal ideas about linear attention, about test and training, about attention, and etc.
Yeah, I actually have a question.
Yep, let's start from your question.
Yeah, thanks for the great talk. I know that in this field, like how to memorize and how to handle like the long context is like the first step. But do you think that's the whole story for test time training?
No,
Should we more care about like to filter out what we should learn instead of just like memorize each token, memorize a long token?
yeah, yeah. So this is actually a very good question. I think about this in the summer. Let me think about how to rephrase this question. So let me rephrase from this perspective. Uh, Memory in humans means a lot of things, right? Humans have short-term memory, long-term memory, have hierarchy of memories, and they have consciousness. And for example, every time when you sleep, you will say, "Hey, what's important today? What have I done wrong? What should I have done more correctly?" You have a lot of reflection, which is basically you are managing your memory. You have a lot of hierarchy systems, and when we are designing neural networks with RN, which is some type of memory, with attention, some type of memory.
Mm.
Should we have some similar strategies? Or even should we have also combined with RG, retrieval augmented generation? Or should we also, there are a lot of context management stuff, like say, hey, the model read this book, the model gonna summarize this book into a paragraph and then remove the book from the KV cache. Right? There are a lot of operations. Do we need all of them? And how should we use all of them? So uh, my feeling is this. There are one type of so we need first to build a working memory and the long-term memory for neural network. I think working memory is softmax attention. Working memory is limited by some sequence length. That sequence length is limited by your hardware. How many sequence length you can do attention for in that hardware. For example, that sequence length typically maybe 1 million tokens on current language models. And beyond this 1 million token context length, you use RN to handle long-term memory. And such long-term memory is compressive. It's lossy. It's compressive. It can only memorize some abstract semantics. It cannot memorize precise details. So you have a working memory and you have a long-term memory. And that's step one. Second step. So step one is basically about you have two memory mechanisms that can work together and it can work very, very well, maybe up to 1 billion tokens or up to something. You can memorize something roughly. Step two, you need context management. So you need the model maybe to do some reflection and say, hey, today I did this. This doesn't work. Today I code together with Tianyuan and we realize this doesn't work because of this. Then summarize into some piece of more informative information and put in your context. And this context of management is not only for making the working memory more efficient. I think it's also about long-term in-context learning. Because I think if you have a long memory and you do a lot of reflections, reinforcement learning, learn to do reflections, you can learn in context. You can do some things like evolvements over time. And I think that's how human learns through time. It's all done by some reflection and embedded in your memory system. Embedding that piece of reflection in your memory system.
Right.
And
But
yeah, sorry. Can I add one point? So speaking of this, you show some experiments in language model where you experimented with fixed trunk with 2048, right? And you also added a adaptive sliding window on top of it. So my question is sliding window plus the fixed trunk equivalent to adaptive trunk? And if that is equivalent, then does that mean you are actually using what you call context, memory, and reflection in
No,
that case?
no. This is not the same thing. The context management I was thinking about is suppose I'm doing something with my language model. Suppose I'm doing a research brainstorm with my language model. We get some idea. And tomorrow I tell the language model, I implemented some of the idea. I realize it's wrong. The reason it's wrong then it ignored this. It assumed this. This is wrong. And the language model will say, hey, oh, you're right. We didn't consider this. Maybe next time when we are thinking problem of similar structure, we should think about this. And I think that's context management, right? You do some reflection and you delete the memory through your working memory, pass it to your compressor memory. Compressor memory basically says, oh, we have done this, but I forgot the details. But you keep the reflection in your context, in your working memory.
I see.
Some example like this. Maybe you can do much better than this. This is just something out of my mind at step one. I think that's context management. It's external to your neural architecture, right?
I see. Okay, I see. Makes sense.
yeah, thanks for the explanation. I think that that makes lots of sense. But as a following question, because we are in the robotics field, so if everything that the context management is the second step. The first step is the model must handle some very long context thing, must use the very large model. Then how should that motivate the robotics field? Will the robotics must apply those huge model first and then be able to add this context management idea on top of it, or this is total irrelevant? Yeah.
Oh, so I think with my limited understanding, I think for robotics, long-term compressive memory is important. If you want a robot to do some tasks, and that task require hours of operation. Ideally, you have a video stream as input, right? You have some video sensors, and it's a streaming input. And 1 hours of input videos at a low resolution, it's about 3 million tokens from one camera. if you do about 2 FPS or 1 FPS. If you do high FPS, it can easily go beyond 10 million tokens. And if you like robot to do that task, it's possibly 10 million tokens.
Mm.
I know that a lot of VLA today are Markov. It doesn't have memories. It just look at the past maybe 1 frame or 2 frames.
Right.
But I think this is not because more memory is bad. This is because the current training paradigm, data set, etc., limits the potential of these long context models. But I don't know if you think about a robot can do things like for 2 hours or even for a day. It's definitely a long memory scenario. And the majority of the tokens can be removed, right? Majority of the tokens compressive is not informative. So this is actually a very good use case for RNN, right? You don't need full attention to keep every tokens of every previous seconds. You can do RNN with compressive memory for this.
Right.
So that's my first comment. I think it will be useful because a lot of robotics application do require hours of video stream as input.
Mm.
The second comment is context management will be harder because the context management example we talked about before is about using language to do thinking and reflection.
Right.
How are you going to do that for multimodal sensory inputs? I don't know. I don't know. Maybe still it's useful. Maybe because, for example, when I learn to ski is about right, control my muscles, and it's hard to describe what my muscles should do, but it also helps to say, oh, maybe I should do this gesture, do this gesture. I don't know. I don't know. It seems harder for the context management step for
Yeah, I
multi.
think for robotics, it's hard because not everything can be easily tokenized, right? So it's
Right.
like you have motor level control and you have multimodal sensory input. It's very hard to find an efficient way to abstract those high-dimensional state and action spaces. So yeah, I think it's still an open question.
Mhm.
Yeah, thanks for the answering. Yeah.
Yeah, by the way, I have one more comment, and just the same topic as the last question.
Mhm.
How do you think of the explicit 3D memory and implicit memory? Like, yeah.
Yeah, that's a good question. I think explicit is not necessary,
Okay.
and also explicit might be a bottleneck for better scalability.
Yeah.
Uh, First, let me answer why it's not necessary. Actually, if you look at, let me share the screen. So first, 3D memory learned implicitly is actually very easy. So all of these novel view rendering results is synthesized by the model. There is no 3D structure. There is no Gaussian point clouds, no etc., no 3D structure. It's all synthesized by the model through interacting with the KV cache, either through attention, either through test time training. And importantly, this model only have parameter of 0.3 billion parameter. 0.3. It's like 3 order magnitude smaller than modern language models. So what I'm showing here is basically says, without 3D structure, it's not that hard to learn 3D. Or it's not that hard for the model to have 3D capabilities. It's actually very easy. So that's step one. Step two, actually let the model be able to output 3D, then use the 3D signal to do some task. This is not end-to-end. End-to-end is much easier for the model. That's what I believe. So I think maybe if you want 3D in the bottleneck, it may limit your scalability of the full pipeline.
What do you think of a robot doing a task in indoor scenery? For example, some people will make the robot memorize the 3D map in its memory, something, but that has to be explicit, right?
No, you can. The model can have some capability by memorizing the 3D structure
Okay,
just by memorizing the KV cache.
I see.
So but it doesn't need to know that there are point clouds here, there are point clouds here. It can learn that from interacting with its neural features.
Mhm.
I don't think you need underutilize the model to output the 3D first or take 3D as input.
Do you think this implicit embedded memory can be prompted out like through a language?
I understand your points. I think so. What you're saying that you don't have supervision for 3D, but you directly let the model do some 3D heavy task. And after that, the feature, if the model is able to complete that task, the model should learn something about 3D. Then can prompt the model to output some 3D. I think you can, but if you add that loss during training, maybe your full pipeline performance will drop because the model understands 3D the way different from humans.
Yeah.
And if you try to align that representation, your performance will drop. That's my thought.
I see.
I might think of a case where 3D is useful is about sim to real because sim to real you can use point clouds, which the domain gap might be smaller than RGB images.
Right. Thanks.
Okay, nice. If no other question, we would like to thank Tianyuan for the great talk and Q&A session. We have 4 follow-up one-on-one slots after the lunch break. See you there. Thank you very much.
Thanks for hosting and very nice to be here.
Thank you.
Very